Hearing part two, equilibrium. All right, so there are specific ranges of frequencies that we can hear in. A frequency is the pitch. So a higher frequency has a higher pitch, a lower frequency has a lower pitch, and it's the number of waves occurring in a period, which is a certain time for wavelengths. It's very physics. So the human hearing range is 20 hertz to 20,000 hertz, and we're most sensitive in that mid-range of 2,000 to 3,000 hertz. That's why our frequency is in between that range. Dogs can hear up to 50,000 hertz, and bats and dolphins can hear up to 200,000 hertz, so they're much more sensitive to those higher frequencies. There's two types of deafness, and we actually tested these with the Ryan's and the Weber's test the other day. So conductive deafness is when the eardrums or the ossicles are not working properly. They're not vibrating in response to those sound waves. And we tested that with the Ryan's test via bone conduction and then air conduction. If you didn't hear it via air conduction after bone conduction, then you probably have some damage to your middle ear. And then there's sensory neural deafness, which is damage to your inner ear, damage to your cranial nerve, damage to the brain, or damage to the hair cells. So it can be any of those things. And what it's testing is if the sound localizes in one ear, meaning it's louder in one ear, then you have damage in the opposite ear. So if you heard it symmetrical in both ears, then you're fine. If it kind of localized to one ear, then the other ear has some damage. And that's typical. So a lot of people have damage to the hair cells in their ears because we listen to really loud music, or we go to concerts, or like you fire guns without earmuffs, and that causes the hair cells to effectively become damaged, and then they won't vibrate in response to frequencies. So there's two types of equilibrium. There's static equilibrium and dynamic equilibrium. So static equilibrium is the equilibrium you maintain when you are motionless or static. And it detects the position of the head. It helps you maintain stability and posture when the head and body are still, so we're simply standing or sitting. And the organs are located in the vestibule, and it also senses gravity and linear acceleration, so moving forward or backward. If the head and the body move or rotate, then dynamic equilibrium organs will come into play to detect that motion and maintain balance. So the organs for static equilibrium are located in the vestibule. The vestibule is a bony chamber. It's located here, which is in between the semicircular canals and the cochlea. So this whole area right here. Within the vestibule, there's two membranous chambers. There's the utricle, which is located inside here, and there's the saccule, which is located inside here. The utricle is larger, and it communicates with the saccule, and it also communicates with membranous portions of the semicircular canals. And then the saccule communicates with the cochlear duct. And this all helps to maintain static equilibrium. The utricle and the saccule both have a small patch of hair cells, those receptor cells, and support cells, and they're called the macula, and it's located on the walls of those chambers. So when your head is upright, the hairs of the macula and macula in the utricle. So here's our utricle, here's our saccula. So in the utricle, the hairs are projecting vertically, so straight up. And in the saccule, they're projecting horizontally, so straight out. The hairs are in contact with a sheet. It's a gelatinous sheet, and within the gelatin, there's crystals of calcium carbonate. And the purpose of that is to add weight to the gelatin so that when your head moves, the gelatin has a response greater to gravity. And around the hair cells, there are sensory receptors, and then there's also the nerve fibers wrapped around those bases so that they can send the impulse to the brain. So gravity will stimulate the hair cells to respond. So this needs to have you bending your head forward, backward, or to one side. And when you do that, what happens is the gelatinous mass, which is seen here in kind of a light blue, will move, and that will cause the maculae to tilt. When they tilt, it causes the hairs to bend, and that's the mechanoreceptors. So they're stimulated, and then they will signal nerve fibers. So here we have all their nerve fibers branching off. All those nerve fibers will then send the impulse to the CNS, which informs the brain of the head's position. And then what happens in the brain is it will send motor impulses to skeletal muscles to contract or relax to maintain balance. So maybe you need to move a foot forward to maintain balance, or a foot out to the side, or put your hands out to maintain your balance. The maculae also aid in dynamic equilibrium. So when your head or your body is thrust forward or backward really abruptly, the gelatinous mass will lag slightly because of momentum. So so your body will move forward in this direction, but this gelatinous mass will lag a little, so it will kind of stay here for a bit. And that will cause the hair cells to bend and be stimulated, and that will tell the brain to help it detect movements such as falling, and it'll also help you maintain posture while you're walking. Here's some animations for static equilibrium you can go ahead and watch. So dynamic equilibrium is maintaining equilibrium while you're in motion. And there are 3 canals at right angles. These are the semicircular canals, and they're all occupying different planes in space. And they're in the 3 planes of your body. So there's the vertical, horizontal, and the sagittal, I suppose we would call it, or the X, Y, and Z axes. So you can see here so this square is a plane going up and down, and then we have a plane right angled to that, and then our X plane is going horizontal to that. And the blue, red, and black C's are the semicircular canals. So you can see each canal occupies a different plane in our body. And we need that so that we can detect different movements and exactly where they're coming from. So suspended in the perilymph of the bony canal is the membranous semicircular canal that ends in a swelling called the ampulla. And the ampulla, so we can see here we have these swellings. There are 3, and they're communicating with the utricle of the vestibule for static equilibrium. So the ampulla contains septum, and that crosses the tube and houses a sensory organ, and that organ is called the crista ampullaris, and that is where our sensory hair cells and support cells are. So it's very similar to the macula of the utricle and saccule in that the hairs extend upward into a gelatinous mass. They're also connected to nerve fibers that connect directly to the vestibulocochlear nerve, which is the nerve that transmits the impulses directly from the ear to the brain. So when the head or torso moves, the semicircular canals move as well, but the fluid inside doesn't initially, and this is due to inertia. So what happens is the gelatinous structure will bend in a direction opposite of the head and torso movement because of that lag, and then the hairs will bend, and this stimulates hair cells to signal their nerve fibers, and then that will send the impulse to the brain. So because of the orientation of the canals, because the canals are in the approximate 3 planes of the body, any movement in a different direction will affect different combinations of those canals. So maybe you're going diagonal, so it will affect the vertical and the horizontal planes. And your brain will interpret these impulses as originating from those combinations so that they can determine the movements, if the movements are coming from different directions. So the impulse is sent from the vestibulocochlear nerve, and it travels to the vestibular area of the temporal lobe to interpret what's happening, also to the cerebellum to induce motor movement, and also the muscles of the eyes aid in this in case we need to move our eyes to detect anything else around us. Also, eyes detect changes in posture, and they can replace the organs of equilibrium, so the utricle and the saccule and the crista ampullae. Because we can fully rely on them to maintain posture. That's why when you guys were balancing on one foot, we took away your equilibrium by plugging your ears, but we left your eyes open, and you tend to do better with that. Whereas if we plug your ears and close your eyes, then you lose equilibrium much faster. So here's just a summary of how we control balance. So the signals from the vestibule and the semicircular canals are sent to the cerebellum, which is responsible for equilibrium and balance. The eyes also help maintain balance, and proprioceptors, especially in your neck, help to send info to the cerebellum on the orientation of your body parts. So nystagmus is when your eyes jiggle back and forth. This is not after we spun the person and their eyes were jiggling. This is a involuntary eye movement that is always occurring. It is similar to when we spun them and their eyes were jiggling because they were trying to fix on an object to help interpret their balance. But because their inner ear was still rotating, not their inner ear, but because the equilibrium was all thrown off, they were still sending impulses to their brain that said you are still in motion even though they are not in motion. So they're trying to align the two to create balance. Nystagmus typically develops during infancy. It can also develop later in life, and it will result in reduced or limited vision. Motion sickness is when the inner ear and the visual stimuli aren't matching. So your inner ear is telling you that you are motionless. So if you're in a car, your body isn't moving, but the passing scenery tells you that you are moving. So your visual stimuli aren't matching. And what happens is it stimulates dizziness and nausea as a reflex to warn you that something is wrong with your brain and that you should stop doing what you're doing. So to get rid of motion sickness, you can close your eyes or look at far distant objects because far distant objects aren't moving as quickly as closer objects. There's also head rushes, also called vertigo, and this is when dizziness or you see black or stars can occur when you stand up too quickly. And this is because when you stand up too fast, you bend the hairs in the ampulla very quickly and then you stop. And so what happens is your ampulla are sensing motion when there is no motion because of inertia. So the ampulla get bent very quickly and that triggers a dizzy reflex to tell your brain that something isn't right. And also the sinus fluid in your head presses on nerves because of that really fast motion. And that causes, depending on where the sinus fluid is pressing, it can cause you to see black or see stars.